Hey, hello, my people. I hope we're doing well today. This is our first uh, new unit for the year, and we're going to launch into a chapter on integration techniques. Now, thus far, you've basically only dealt with integration rules that you've learned, which were basically the flip side of differentiation, which is great because really what you're doing is you're undoing differentiation. And usually what you're looking for is you're looking for an integrand. You're looking for that integrand to be a recognizable derivative from the list from when you did differentiation. Uh, the only exception to that was when you ran into U sub, right? And basically did integration by substitution. That was the first time you ran into integrals that whose integrand was not a recognizable derivative, and you therefore had to use substitution to change the form. We're going to learn several other techniques to deal with non-integrable inter. Gosh, okay. Basically, integrals that you can't do based in the form that they're in at present. Okay, so let's consider, and if you're watching this after class, then of course this is the same example that we did in class. Consider the integral x e to the x. Now that is not a recognizable integral, but it is part of a recognizable, it's not a recognizable derivative in the integrand, but it is the part of a recognizable derivative right here, right? So it's not the whole thing, but it's part of it. Okay, well maybe that'll actually wind up helping. Okay, now we know that integration and differentiation are operations and they're inverses of each other. So let's go ahead and integrate both sides. And when I integrate the left side, the d dx and the integral with the dx differential cancel each other out, and I'm just left with the x e to the x. On the right-hand side, when I integrate with respect to dx, I can do it term by term, and now I have two independent integrals. Well, that's kind of neat because that one right there is the one that I was given at the very beginning, right? And so if I shuffle the terms around just a little bit, I can solve for this integral x e to the x dx, and it winds up being equal to this expression. Okay, well, if I can't integrate that, I'll integrate that instead. Okay, so basically what's going on here is we're actually using the product rule, and we're using the product rule in order to shuffle things around such that when I'm given something of this form, I don't seek to integrate that, I seek to integrate an equivalent expression. Okay. And so when I go ahead and integrate that negative integral e to the x dx, I of course get e to the x plus c. And basically this is the answer for that integral. And all I had to do was recognize the fact that it could indeed be a part of a recognizable derivative and not the entire derivative in and of itself. Now, that is a specific example. But we can use the product rule to basically universalize this, and that's what we're going to do. Now, if I'm given u and v, and I need to differentiate that product, I'm going to differentiate u v prime plus u prime v. Okay, well, let's go ahead and integrate both sides, and that leaves me with the product is equal to the sum of these two integrals. Well, let's go ahead and adjust the notation just a little bit. And so I have u times v is equal to the integral of u dv plus v du. And if I shuffle those around a little bit, just like I did before, I'm going to get the integral of u dv is equal to uv minus the integral of v du. Okay? And that basically is what we're going to be doing. We're going to be using this right here in order to sort of break integrals apart and basically figure out how to find an equivalent expression that I can integrate. Okay, Well, all of that is wonderful, but what we need to do now is we need to actually attend to specific examples. So let's go ahead and let's look at this one. Now, I need to find a u and I need to find a dv. Now, the u is usually, especially when you have something like this that is a polynomial factor, it's usually going to be that right there, okay? And so basically let's go ahead and designate u as x. And then let's designate e to the 2x dx as my dv. Now what needs to happen now is I need to differentiate the u. I need to anti-differentiate the dv. And when I do that, of course, I'm asking what e to the 2x is the derivative of, and that shouldn't be too hard to remember that it's 1/2 e to the 2x. All right? Now, what I'm going to be doing from here is if this right here, okay, if this right here is my u, and this right here is my dv, I need to basically find a uv minus v du. And I have all those right here. So my uv is 1/2 x e to the 2x minus, and then v du, these that are on the diagonal right here. Well, that 1/2 that's in the v right here can be popped out in front, and then e to the 2x dx. And e to the 2x I already know is integrable because I just took the antiderivative over here in the midst of designating u and dv and finding du and v. So I have 1/2 times the antiderivative, or the integral of e to the 2x, so it's going to wind up being 1/4 e to the 2x plus c. And if I want to clean it up, of course I can factor out a 1/2 e to the 2x, and I'm going to get x minus 1/2 plus c, or something like that, okay? And there we go. Now this is one of those things where it's just going to take some practice, and so let's just keep practicing, okay? I need to find a u and a dv. Now here's the thing, usually, and this isn't always the case, but a lot of the times, especially on these easier ones, you are going to designate u as the thing that you want to get rid of, the thing that you want to evaporate. Notice here I designated u as the x because I know the moment that I take the derivative of x, it basically becomes 1, and all I'm left with is the differential right here. I'm going to use the same strategy down here for this one. I'm going to designate my u as x, right? And then my dv right here, I'm going to designate as the cosine x dx. So cosine x dx. Now when I anti-differentiate cosine, it should come as no surprise at that sign. And when I differentiate x, I'm going to get dx. Now remember, what I'm looking for now is I've designated my u and my dv, and so remember the integral of u dv is uv minus the integral of v du. Okay, well, my u and my v are x and sine x, and my v du is sine x dx. I know how to anti-differentiate sine. Sine is the derivative of negative cosine, and the negative of the negative cosine is going to cancel with that negative right there and become plus cosine x plus c. And if you're saying to yourself, surely not, surely that can't work, okay, well, I mean, you've just integrated, so the way that you check your answer is you differentiate. If I have y is equal to x sine x plus cosine x plus some constant, which I won't put because we know it's going to wind up becoming 0. This is the product rule, and so I get the first times the derivative of the second plus the derivative of the first times the second, and then I need to add the derivative of that second term, which is negative sine x. Oh my gosh, those cancel out, and will you look at that? That was my original integrand, okay? And so, and thing is, like, you know, you don't want to check every single one as you do it, but checking them every once in a while will just sort of, you know, assure you that you're on the right track. Alrighty, let's go ahead and let's look at this one. Now this one winds up being a little, basically it's kind of the same, but this is one of those things where you go, okay, well, the last two, I took the x term and I designated it as u, okay? Well, that's what I'm going to do this time, except, I mean, it's x to the 1/2, but sure. The problem is that you would then have to designate natural log x dx as your dv. And how do you integrate? How do you anti-differentiate that? Well, the answer is you really can't. But I know that if I designate my u as natural log x, that it doesn't evaporate into 1 like x did, but I know that in the differentiation, the natural log aspect of it goes away, and I'm left with 1 over x dx. And so if I want to designate that as my u, then x to the 1/2 dx is my dv. And basically, when I anti-differentiate, I add 1 to the exponent, divide by that new exponent. That new exponent is, that denominator is going to be 3/2. So basically, I'm multiplying by 2/3. So 2/3 x to the 3/2. Okay, well, if that's the case, then my uv is 2/3 x to the 3/2 natural log x, and then my vdu is here. Well, this is x to the -1. This is x to the 3/2, which basically reduces to x to the 1/2. And so I'm 2/3 integral x to the 1/2 dx. Well, I know how x to the 1/2 dx integrates, because that's what I designated my dv. So I've already done that work once. I simply have to do it again. And when basically this integral becomes 2/3 x to the 3/2, the 2/3 and the 2/3 combine to make 4/9 x to the 3/2, and of course the obligatory plus c. And if the circumstances are dictated, you can pull out a 2/3 x to the 3/2, and you're left with natural log x minus 2/3 or something like that. And of course, you just want to leave it in the form that's going to be the most useful for what you're going to do next. Okay. Now this one appears to only have one part. Okay, but it actually is more than that. Okay, because remember that dx is actually part of that integrand. And therefore, again, let's go ahead on this one and designate u as natural log of x, and then dv as just dx. Well, that means that I'm looking for something whose derivative is 1. So v is just x, and du becomes 1 over x dx. Now when I'm looking for my u times v, it's x, natural log x, minus the integral of v du. Well, the 1 over x and the x cancel each other out, and I'm just left with the integral of dx. Well, I know how to integrate that because I just anti-differentiated it over here, and I'm left with x natural log x minus x plus c. Okay. Now, this winds up, and the thing is that if you designate the wrong u and dv, you're just not going to go anywhere, and that's going to be an indication that you need to back up to the problem and redesignate and try again. Okay, And so don't get frustrated when you do that. It actually does take a little bit of practice in order to, get pretty good at anticipating what's going to go on. Now here again, this one is going to be much like our natural log one from the previous page, because it looks like there's simply one thing in the integrand. But there's not. There's dx. So when there's only one thing in the integrand, you know that that's going to be your u. And you know that your dv is just going to be the differential that's there. So v becomes x, and du becomes 1 over the square root of 1 minus x squared. And I guess you can put your dx up here in the numerator, or you can plop it right next to it. It doesn't really matter. So what we get here is my uv is x arc sine x minus, and here's the integral. We're going to go ahead and put the x up here in the numerator since I'm combining v and du. 1 minus x squared dx. And if you're thinking to yourself, gosh, that looks like an old u sub problem, you'd be right. Okay? Now that you have it in this form, I didn't necessarily say that the integration on that piece right there would be incredibly straightforward. I just said that it would be possible, right? And so in order to got to do some integration by substitution. And the way that you do that, of course, is, let's go over here. Since we've already used u up here, I mean, we usually call it u sub, but there's nothing magical about u. We can use t. So let's and that's L-E-T. Sorry, sometimes that looks a little bit like a 6t, but it's let t equal 1 minus x squared. So really, instead of doing u sub, we're doing t sub. But like I said, nothing magical about the variable. It's just one of them we usually use. So what we have here is we're going to go ahead and get dt, and that's negative 2x dx. Well, if I want negative 2x, I need a negative 2 up here. Well, if I put a negative 2 up here, I need to put a negative 1/2 out in front. So what happens here is I get that, okay? Go ahead and do a little u sub. I know that if I'm integrating, that's going to be, t to the negative 1/2 dt. And when that happens, I know that, basically I'm going to get t to the 1/2 over 1/2, right? T to the 1/2 over 1/2, or 2t to the 1/2. Well, that 2, so this is sort of just being done on the side. That 2t to the 1/2 is actually 1 minus x squared to the 1/2. And the 2 and the 1/2 are going to cancel out when I plug it back in here. I'll go ahead and show just, plugging it back in. And I'm going to get 1 minus x squared to the 1/2 plus c. Those cancel out, and I'm left with x arc sine x plus the square root of 1 minus x squared plus c. Ta-da! Alrighty. Let's start the next video with this problem right here. I don't want to do this one and then stop because the first one on the next page is actually related to it. There'll be a couple more videos, but as always, if you have any questions, please do shoot me an email and let me know. All right, bye.